First, we will learn how to draw Lewis electron dot structures. We have earlier seen how to draw the Lewis dot structures of simple diatomic molecules, that is, molecules having only two atoms. Drawing the Lewis dot structures for diatomic molecules was intuitive and can be guided alone by the octet rule. However, for molecules having more than two atoms, it may get really complicated. To make this easier, we follow a set of guidelines to draw the Lewis dot structures of molecules with more than two atoms. Once you draw these molecules several hundreds of times, even these molecules can also be drawn intuitively. But at the beginning, I strongly encourage you to stick to the guidelines that are given. Before discussing the guidelines, remember that you will be given the molecular formula of the molecule or ion, and you will be asked to determine its Lewis electron dot structure. Place the atom with the lowest electronegativity in the center, unless you were instructed otherwise, or you were given an arrangement of atoms for a molecule with more than one central atom. You have already learned how the electronegativity changes across the period and down the group. That will really come in handy to pick the atom with the lowest electronegativity. Guideline number 2. Find the total number of valence electrons in the molecule or ion given. The way we do it is, find the sum of the valence electrons of all the atoms, and if there is a negative charge on the ion, you add one electron, and if there is a positive charge on the ion, you subtract an electron. We have already learned how to determine the valence electrons in a given atom from its group A number. All we are doing here is finding out the valence electrons in all the atoms of the given molecule or ion and add them up. Guideline 3. Connect all the atoms to the central atom with single bonds or lines using the following. A. Hydrogen and halogens usually only form a single bond. Halogens are elements in group 7A. Elements in the second period form the following number of bonds. Boron has 3 electrons in its valence shell, therefore it can form 3 bonds. Carbon has 4 valence electrons, therefore it can form 4 bonds. Nitrogen, even though it has 5 electrons, 2 of the electrons are already paired, therefore it can form 3 bonds. Oxygen, it has 6 valence electrons. There are 2 pairs of electrons and 2 single electrons, so therefore oxygen can form 2 bonds. Fluorine has 7 valence electrons, that is 3 pairs of electrons and 1 single electron. Therefore, it forms 1 bond. The next guideline, subtract 2 electrons from the total number of valence electrons for each line or bond you have drawn. 4. Add remaining electrons to the terminal atoms in pairs, giving each atom an octet. Place any remaining electrons on the central atom. 5. If the central atom does not have an octet configuration, form multiple bonds to terminal atoms. If the central atom has less than 8 electrons, move a lone pair from an outside atom to make a bond pair between the terminal atom and the central atom. Repeat this until the central atom gets at least 8 electrons. Let us now put these guidelines to use and draw the Lewis dot structures of some molecules and ions. Let us do some examples. The first example is draw the Lewis dot structure of NF3. The first rule says that we need to keep the atom with the least electronegativity in the center. We have two atoms given in the molecular formula, nitrogen and fluorine. Both of them are in the same group, and nitrogen is to the left and fluorine is to the right. Therefore, nitrogen has least electronegativity. I'm going to place nitrogen in the middle and place the remaining fluorines on the three sides of the nitrogen. That is the first rule. The second guideline is count the total number of valence electrons in the molecule. Nitrogen belongs to group 5A. Therefore, it has 5 valence electrons. Fluorine belongs to group 7A. Therefore, it has 7 valence electrons. However, we have 3 fluorines, so I'm going to multiply these 7 valence electrons with 3. So in total, we have 21 plus 5, that is 26 valence electrons. According to the third rule, we need to connect the terminal atoms, that are atoms on the side, to the central atom, that is the atom in the middle, using the valence electrons that we have counted, first by single lines or bonds. I'm going to connect each of the terminal fluorine atoms to the central nitrogen atom. Each of these bonds cost 2 electrons. So in total, I have used up 6 valence electrons. So now I have 20 valence electrons that are left over. According to the fourth guideline, I'm going to use these remaining electrons and place them on terminal atoms as pairs until each of the terminal atom becomes an octet. So I'm going to start with one of the fluorines, place the electrons in pairs until that fluorine has become an octet. Now it has 8 electrons, so I move on to the next fluorine atom and repeat the same process. Now all the fluorine atoms have attained octet configuration, and I used up 18 valence electrons in doing so. So I still have 2 valence electrons that are left over. I am going to place those 2 valence electrons on the central atom until it becomes an octet electronic configuration. Nitrogen already has 3 bonding pairs, that is 6 valence electrons. So I am going to add the remaining 2 to give it an octet electronic configuration. Now each of the bonded atoms have 8 electrons in its valence shell. Therefore, this is a Lewis dot structure of NF3. The next example that we are going to do is an ion, which is PCl2 minus ion. We will follow the same guidelines. First, we will place the atom with the least electronegativity in the center. If you look at the periodic table, phosphorus has lower electronegativity than chlorine. So I'm going to place phosphorus in the middle and the chlorines on either side of phosphorus. Next, count the total number of valence electrons in the molecule or ion. Phosphorus belongs to group 5A, therefore it has 5 valence electrons. Chlorine belongs to group 7A, therefore it has 7 valence electrons. However, we have 2 chlorines in the formula, so I'm going to multiply that number with 2. On top of these valence electrons, the ion has a negative charge on it. And according to the rules, whenever we have a negative charge, you add an extra electron for each negative charge. So overall charge on the ion is -1. Therefore, I am going to add 1 valence electrons to the total. So in total, I have 5 plus 14, that is 19 plus 1, 20 valence electrons. I am going to use these valence electrons first to place as a single bonds between the central atom and the terminal atom. So there are 2 chlorine atoms. I am going to connect both the chlorines to the phosphorus. Each bond or line uses 2 electrons. So there are 2 bonds. So in total, I used up 4 valence electrons. So there are 16 leftover valence electrons. Now I'm going to use these remaining valence electrons and place them on the terminal atoms first as pairs until each of the terminal atoms becomes an octet. Now as you can see, each of the chlorine atoms are already bonded to phosphorus using 1 single bond. That means this chlorine has 2 electrons in it and this chlorine has 2 electrons in it. So each of the chlorines, I can place 6 more electrons on them. I'm going to do that. 1, 2, 3, 4, 5, 6, and the other chlorine 1, 2, 3, 4, 5, 6. So I have used up 12 electrons in doing so. So there are 4 valence electrons that are remaining. I'm going to use the remaining electrons to give an octet configuration to the central atom. As you can see, phosphorus already formed 2 single bonds with each of the chlorine atoms. And we know that a single bond contains 2 electrons. So that means phosphorus already has 4 electrons. So I can give a maximum of 4 more electrons to this phosphorus, and that's exactly how many electrons I have. 1, 2, 3, 4. So I used up all the valence electrons, and each of the atoms in the given ion now have an octet electronic configuration. Remember that we still have 1 electron more than the electrons contributed by the individual atoms. Therefore, it has a negative charge overall. This is the Lewis dot structure of PCl2- ion. Next example, we have CH4O. There are 3 different types of atoms, and this is an example where you have more than 1 central atom. First, here are the electronegativity values of all 3 atoms. Hydrogen is the atom with least electronegativity. However, I cannot place hydrogen in the middle or as a central atom because hydrogen forms a maximum of 1 bond. Therefore, the atom with the next lowest electronegativity is carbon, acts as a central atom. Because the hydrogens can only form 1 bond, I am going to place the hydrogens at the sides. Carbon atom forms 4 bonds. I am going to place the carbon in the middle, and oxygen, because it forms 2 bonds, I am going to place the oxygen in between the carbon and hydrogen. Next, let us count electrons. Hydrogen belongs to group 1a, so it has 1 valence electron. However, there are 4 such hydrogens, so I am going to multiply it with 4. Oxygen belongs to group 6a, so it has 6 valence electrons. And carbon belongs to 4a, so it has 4 valence electrons. In total, I have 14 valence electrons. First, I am going to use these valence electrons to connect the central atom to the terminal atoms by a single bond. I have placed 5 bonds, therefore I have used a total of 10 valence electrons. So there are 4 valence electrons that are remaining. I am going to place these remaining electrons on the terminal atoms, and once the terminal atoms attains the octet configuration, I move on to the central atom. In this case, the terminal atoms are hydrogen, which have a duplet configuration and are already stable. Next, I move on to oxygen. Oxygen has 2 bonds, that means 4 electrons overall. Therefore, it is short of 4 electrons, which is exactly what I have. Therefore, I am going to place these 4 electrons as 2 electron pairs on oxygen. Now the oxygen atom has octet electronic configuration, and we have used up all the valence electrons. Let us now verify if each of the bonded atoms has an octet configuration, or in case of hydrogen, a duplet configuration. Each of the hydrogen atoms form one bond, that means they have a duplet electronic configuration. Carbon forms 4 single bonds, that means it has an octet electronic configuration. Oxygen forms 2 single bonds, and it has 2 non-bonding electron pairs. So overall, oxygen also has 8 valence electrons. This is the final Lewis dot structure of CH4O. The next molecule is C2H4. As we learned earlier, hydrogens cannot be placed as central atom. So I am going to place hydrogens on the terminal and carbons in the middle. Next, we count the total number of valence electrons. Hydrogen belongs to group 1A, therefore it has 1 valence electrons. There are 4 hydrogens, so I am going to multiply that 1 electron with 4. Carbon belongs to group 4A, so it has 4 valence electrons. And there are 2 carbons, so I am going to multiply that with 2. Overall, I have 8 plus 4, that is 12 valence electrons. I will use these valence electrons to connect the terminal atoms to the central atom by a single bond. So I have placed 5 single bonds, which costs me 10 valence electrons. So there are 2 valence electrons that are remaining. I cannot place these remaining 2 electrons as electron pairs on the terminal atoms, which are hydrogens, because hydrogens already have a stable duplet configuration. Now let's look at the central atoms. Both the carbon atoms have 3 bonds each. That means each of them have 6 valence electrons. To satisfy both the carbons, I need 4 valence electrons. However, I have only 2 valence electrons that are left over. I am going to give those 2 valence electrons to one of the carbon atoms. Now the carbon atom that gets that 2 electron has an octet configuration. The other carbon atom has only 6 valence electrons. What are we supposed to do now? We are going to use the 5th guideline. According to the 5th guideline, after we use all the remaining valence electron, if the central atom still has less than 8 electrons, move a lone pair, that is non-bonding electron pair, from an outside atom to make multiple bonds until the central atom becomes an octet. I'm going to do exactly that and transfer one of the non-bonding electron pairs on the carbon as a multiple bond between the two carbon atoms. The carbon atom from which I took away the non-bonding electron pair did not lose any electrons because the non-bonding electron pair got converted into a bonding electron pair. It still has overall 8 electrons or octet configuration. The other carbon which got a new bond now has 2 extra electrons than before. If you count the total number of valence electrons around this carbon, now it has 4 bond pairs, that means 8 valence electrons. So at the end, we verify if each of the atoms have either an octet configuration or a duplet configuration in case of hydrogens. As we see, all the 4 hydrogens have 1 bond each, that means a duplet configuration, and the remaining 2 carbons have 4 bonds each, that is octet configuration. So this is the final Lewis dot structure of C2H4. Next example, NO+. There are 2 types of atoms here, nitrogen and oxygen. I am going to place the atom with the least electronegativity in the center, that is nitrogen, and oxygen on the terminal. Because this ion has only 2 atoms, I am going to label the nitrogen as central atom and oxygen as terminal atom. Next, I am going to count the total number of valence electrons in the ion. Nitrogen belongs to group 5A, so it has 5 valence electrons. Oxygen belongs to group 6A, it has 6 valence electrons, and there is a net positive charge on the ion, which means I have to subtract 1 electron. So the total number of valence electrons in the ion are 5 plus 6 minus 1 comes out to be 10 valence electrons. Next, I am going to use these valence electrons to connect the central atom to the terminal atom using single bonds. So I have used up 2 valence electrons. There are 8 valence electrons remaining. The remaining electrons first go on to the terminal atom, that is oxygen, as pairs until the terminal atom reaches octet configuration. Oxygen already has 1 bond, that is 2 electrons, so I can place 6 valence electrons in pairs. So I have used 6 valence electrons in total for that, and I have 2 valence electrons that are remaining, which I will place on nitrogen atom, which is the central atom, as electron pairs. I have used up all the valence electrons, but still nitrogen, which is the central atom, did not attain octet configuration. Therefore, I am going to transfer the electron pairs from the terminal atom as a multiple bond between the central atom and the terminal atom until the central atom gets an octet electronic configuration. First, I am going to transfer 1 electron pair. That increases the number of valence electrons in nitrogen to a total of 6 valence electrons, but it is still not octet. Next, I am going to transfer another electron pair from oxygen as a multiple bond. Now that increases the total number of valence electrons in nitrogen to 8. Both the nitrogen and oxygen now have octet configuration. At the end, we have to represent the overall positive charge on the NO+ ion on the Lewis dot structure, which gives us the final Lewis dot structure of NO+.